I'm Charles Wilson, Staff Product Cybersecurity Architect at Torque Robotics. This presentation will cover an overview of threat model analysis. This diagram shows the overall AVCDL training path. If you're taking this training, it's assumed that you've already completed the AVCDL overview training, and additionally, that you've completed the Requirements Taxonomy, Security Requirements, Secure Design Principles, Apply Secure Design, and Threat Prioritization Plan training. Additionally, you should have completed the Threat Modeling Overview and Model Creation trainings. This training will cover threat model analysis. Before getting into threat model analysis, let's briefly review where it fits in the overall threat modeling process. Here's the threat modeling process with its three individual activities: model creation, model analysis, and threat candidate triage. Let's consider the model analysis activity. In the threat model analysis activity, the threat modeling SME takes the threat model and the updated development requirements and performs an analysis, which results in the creation of a set of threat candidates. Returning to the NIST threat modeling lifecycle, we see that the threat modeling analysis corresponds to the identification activity of that lifecycle. Now let's work our way through the same example used in the threat model creation activity to illustrate how the threat modeling analysis activity is undertaken. Recall that from the threat modeling model creation video, we took a simple example system and created 3 increasingly refined DFDs from it. Working with the development SME, we took those DFDs and extracted features from them. This was done for the data flows, resources, interactors, boundaries, and finally, the processes. Now let's take a moment to review the generalized cybersecurity approach and how we'll apply it. Here's the general cybersecurity activity workflow. We start with an element feature, which in the case of threat modeling is embodied by the element's threat model. Both the element and activity are constrained by cybersecurity requirements. The activity produces a set of issues where the cybersecurity requirements have been violated. We then either attach those requirements to the element if they're not present, or verify that they're being applied if they're already present. Now keep in mind that you can have constraints in place that aren't actually implemented. We use cybersecurity requirements as constraints in the threat modeling analysis because the AVCDL's threat modeling approach is based on its Cybersecurity Requirements Taxonomy. This is not to say that other bases of threat modeling analysis are not possible, merely that this is the one that's supplied with the AVCDL. For a given organization's threat modeling basis, there will be a set of constraints. Those constraints should have a mapping into the cybersecurity requirements, because the cybersecurity requirements are attached to the functional requirements. And that's what the developers will have to implement. A threat modeling methodology which does not point back to a set of cybersecurity requirements would be neither useful nor implementable by development. Here we are with our cybersecurity requirements. This is not a full set of the AVCDL's cybersecurity requirements, because not all cybersecurity requirements lend themselves to a treatment within the context of threat modeling. Specifically threat modeling where we're using data flow diagrams in order to represent the system. This is a subset of the Global Cybersecurity Requirements Catalog provided with the AVCDL, which can be reasoned on within the context of the information contained in a DFD. It's only about a third of the total number of those global cybersecurity requirements. As we'll see, we're not going to even use all of these because not all of them are going to be applicable to our example. One thing that stands out when looking at this set of requirements in the context of the example is that when the model was created, logging was not included. In going back and checking with the development SME, yes, this system does implement logging. Because of that, before we do our actual analysis, we're going to step back and revise the threat model to include this information. Now let's look at each of the DFDs that were created and see where logging needs to be added. At the highest level, we've established in consultation with the development team that yes, there is an audit log, and it's being used both for the core service and the console interface. And here we see it in place. We have a new resource. We have one-way data flows, both from the core service and the console interface, and no additional boundary here, because as you can see, the audit log is a trusted resource that we own within this context. As is to be expected at level 2, the audit log is actually being managed by a log manager. And this log manager is a third-party piece of software. It's not part of the operating system. Because of that, we have not only the log manager, which is now mediating the audit log, but we have a new boundary layer between the core service, log manager, and console interface. And the last of our big picture DFDs, the level 3 DFD, shows that the log manager is actually using the file system to manage the audit log. We also have an extension of our OS boundary to include not only the database manager, but also the log manager. The only operating system related DFDs we need to update is that of the file system. As mentioned for the level 3 DFD, it's managing the access to the audit log itself. Here we see the update for both the core service and the console interface initialization processes. We see the audit log off of both the core service and the console interface. These are specialized versions of our level 1 DFD. And here's the core service configuration workflow. Both the core service and console interface write to the audit log. And here's the final update needed for our logs, and it's the normal operation workflow, where the core service logs what it's doing. A note here, the web server has been noted previously as being a third-party component, and as we can see, it's not using this audit log. Now, that might be an issue for design, but from the standpoint of what we're considering here in analysis, it doesn't write to the audit log. There's another problem here, and that's one that's been described before to motivate the increased resolution of the level 2 and level 3 DFDs. And that's to add bits and pieces that were missing so that we could see data flows that weren't exposed previously. A different approach not taken when the model was created was that of greater abstraction. We have here a flow or communication sequence that goes from the core service to the web server to the web browser and vice versa. What we don't have is a way to talk about the web browser communicating directly with the core service at that level of abstraction. We've got HTTP communication between the web server and browser, and IPC communication between the server and core service, but nothing showing the application level messaging and data that's being passed between the core service and web browser. So let's look at what that additional workflow looks like. Here's the normal operation at its most abstract level. This is where we can reason about the type of communication that's going on between the core service and the web browser itself. Note that the core service boundary shown here could as easily have been a machine boundary. It's arbitrary which we use. Now that we've gotten the diagramming covered, let's look at what the implications are for the DFD entity lists. Here are the entity updates. As you can see, we've got our resource, the audit log, our process, the log manager, our boundary, the log boundary, and 7 new data flows dealing specifically with the audit log. Additionally, we have our 2 end-to-end communication data flows between the web browser and core service. All of this information gets put into an updated revision of the threat model. You might be wondering why this diversion in order to update the threat model when this is a video about threat model analysis. Well, making sure that you're working with the right information is a normal part of the analysis activity. And updating the model, if it needs to be updated, is critical to performing a proper analysis. You don't just take what's there and blindly do analysis thinking, well, they gave me this, we're just going to go with it. That's not a responsible approach. Now, with all the material up to date, Let's proceed with the analysis. The methodology we'll use to perform the threat modeling analysis is to take the element features as represented in the DFD and the cybersecurity constraint information embodied in the attributes we've collected for each of the entities in that DFD. Our constraints here will be represented by a subset of the cybersecurity requirements. We're going to individually apply the requirements to each of the data flows and reason on them based on the information that we have regarding the data flow, the source and destination, and the trust boundary crossed. Here are all of our operating system DFDs. As mentioned in the model creation video, these are not going to be considered in our analysis, since the focus of our analysis is the element. Be aware that it's important to document these DFDs because we do need to do a separate analysis of the operating system, and these DFDs inform that analysis. That leaves us with the elements workflow DFDs. We could do a complete analysis on each and every one of these data flows, but let's assume that the organization doesn't have infinite time or infinite resources to explore this. The way to get the most impact from your analysis is to look at those things that are at the trust boundaries. As we can see here, the vast number of entities within these workflows are trusted. So what we'll do is focus on those workflows where we have untrusted entities. And the one we're going to be looking at from this example is the normal operation workflow. As mentioned earlier, we're going to take our DFD, just the data flows in this case, and our requirements, and perform an analysis by looking at each of the data flows in turn, considering what the applicable requirements are, and then determining whether those requirements are met. We'll make that determination by looking at the various attributes of each of the data flows, and possibly the attributes of the source and destination entities. Where there's a lack of information or a violation of the requirement, we'll generate an issue. Our focus is on the core service, web server, and web browser data flows, which are crossing either the core service or machine boundaries. The core service is, of course, within the trusted portion of the element. It interacts with the third-party web server, which has a lower trust level, and finally communicates to the outside world, that is, to the web browser. There are 4 data flows, the ones between the core service and web server using the system IPC protocol, and those between the web server and web browser using the HTTP protocol. These protocols have distinct behavioral characteristics. We can't simply say, well, we've got a data flow and things are happening. The protocol is important because it speaks to how we're going to be reasoning on the applicability of the requirements. Now, in reviewing our applicable cybersecurity requirements, we can quickly eliminate all of them until we get to the last 3. These are: communication crossing a trust boundary shall ensure data confidentiality, communication crossing a trust boundary shall ensure data integrity, and communication crossing a trust boundary shall be authenticated. These are the 3 requirements we'll apply to our selected data flows. There's an interesting thing to note here. As we look at the attributes provided in the threat model, we see we have gaps. But, as noted, gaps should not be unexpected. One gap that is unexpected is in ESD10, the core service to web server data flow. We can see that it doesn't show that we have an authenticated source. This is a trusted entity, so it's considered to be authenticated by definition. We're going to have to go back and adjust some of the attributes. Since it doesn't impact the rest of our analysis, we don't have to do anything more elaborate in terms of the threat model itself. Just recognize the fact that there are certain things that may be left out, which are just simple errors, if you will. For the other attributes, however, if something isn't provided, then assume that it's a no. Another thing to note is that the safety criticality attribute informs us as to what we prioritize rather than being something we actually reason on. In the same way that we deprioritize the operating system workflows because all of those flows are handled separately, and we aren't immediately looking at the workflows that are in our trust zone, we look at safety criticality and ask, we've got all of these things, which ones are safety critical? We make sure to address those first because you have to prioritize the issues to be mitigated. The best way to do so is to take the safety critical ones first and address the remainder afterwards. Having done the analysis on these 4 data flows, we found 10 issues. Because of the nature of the issues, they're fairly straightforward to deal with. For the integrity check, we have an attribute for every one of the entities in question, and the integrity check is set to none for all of them. Similarly, encryption is set to none. So the concept of having integrity and confidentiality are basically thrown out the window. When it comes to authentication, we want to ensure that both ends of the data flow are authenticated. And if as shown here with our data, you don't have an assertion that we have authentication on one end or the other, then that's something we need to look into. And so if we look at what information we provide with our issues, we can see that each issue has an ID. And we have a data flow ID to tie back to the data flow we're talking about. We have a Cybersecurity Requirements ID. We have the issue, which is essentially the negation of the requirement. And we have notes, which tell us what in particular is causing the problem. Note that the provided template doesn't have fields for the original functional requirement or any other information, because that's something we can get from the threat model metadata itself. So that covers threat modeling analysis. Let's do a bit of review and talk about lessons learned. When undertaking threat model analysis, it's important to take a practical approach. Remember to review the DFDs. People make mistakes, and DFDs and their creation are no exception. If you find issues in the DFD, correct them right then and there. When you're deciding what to analyze, focus on the elements' workflows. Remember that the operating system flows are something that are common to all elements, and so they should be analyzed together. And if you add a new entity that's going to be working with the operating system, then that should go into the operating system DFD set and analyze there, so that you have a coherent analysis for the operating system itself, regardless of what elements you're adding to it. Perform the analysis ordered by trust level and criticality. Don't spend a lot of effort straight away on things where there's no issue of trust. If an entity is trusted, then its actions cannot be prevented. Focus on those areas where there's a disparity in trust. Special attention needs to be given to the most critical items within that context. Remember that this is not a one-shot activity, and that you have to keep the model and the analysis up to date based on changes to the design. Finally, you don't need special tooling to do threat modeling. It can be really helpful to have automated tools, but trusting automated tools simply because they're automated is not appropriate. You need to know what's being analyzed, you need to understand how the analysis is being undertaken, and you need to appreciate the limitations of the tooling itself. If you can perform threat modeling as shown here in a very manual manner, you can do so in an automated manner. If all you can do is use the automated tool and you don't understand what the fundamentals are, then your effectiveness as a cybersecurity threat modeling SME will be greatly hampered. The materials used to cover this example are in the location shown here. It's important to note that this includes the DFDs, the threat model, and the threat model creation workbook that goes along with it, as well as the updates that we've addressed and the issues that have been identified. All AVCDL material, both in source and distribution forms, are available on our GitHub site, as shown here. Because of the size of the repository, it's recommended that you either clone the repository or download a zip archive of it if you're not familiar with using Git. Instructions for downloading a zip archive are linked to on the repository's front page. Videos covering various aspects of the AVCDL are available on our YouTube channel, as shown here. It's important to note that all AVCDL materials, except for the introductory blog posts, are intended for product cybersecurity engineering practitioners. The final training in the threat modeling sequence is threat candidate triage. And once you've completed all the trainings related to threat modeling, you can proceed to one of the other trainings at this level. These include attack surface analysis, penetration testing, and vulnerability identification. Additionally, if you've completed secure coding and its prerequisites, you can also proceed to static analysis, dynamic analysis, fuzz testing, and Secure Code Review. Here are the references to the source material used in the creation of this presentation. They'll also be included in the video description. Additionally, this presentation's source material will be provided on the AVCDL Git repository.